Hello physics students, we're going to call this part 2 for chapter 8. Alright, we made it to slide 44 in class, so that's why I'm picking up with this video on slide 45. Quick check 8.4. An ice hockey puck is tied by a string to a stake in the ice. The puck is then swung in a circle. What force is producing the centripetal acceleration of the puck? It would be what? It would be the tension in the string. The tension in the string is what is pulling that puck toward the center of the circle that keeps it going in a circular motion. All right, example 8.3. Turning the corner. All right, what is the maximum speed with which a 1,500 kilogram car can make a left turn around a curve of radius 50 meters on a level that is unbanked road without sliding? Okay, so I'm going to imagine this is the car, and I'm staring at the back of the car. Okay, the RTZ plane would be like this. The Z-axis is like this. The T-axis is going into the page. The R-axis is pointing toward the center of the circle. Okay. So we have what acting on this object? We have gravity. And that gravity is going to equal mg, which is 1,500. Times 9.8, which is going to be 14,700. All right, what else do we have? We have a normal force. It's equal to that gravitational force. It's going to be also 14,700. How do I know that? It's because it's on a flat surface. It's not accelerating up into the air. It's not accelerating down into the ground. It's remaining steady on that z-axis, on that flat surface. What else do we have? We have friction. All right. We have rolling friction that would occur on the t-axis that would be pointing outside of the page, but that's really not going to be a factor here. But we also have friction, sliding friction, or we could say static friction, that is keeping this car going around the curve. So I'm imagining the curve going like that, okay? So the positive R-axis points like that. So we have a frictional force that is pointing toward the center of the circle, keeping it from going in a straight line. And that frictional force, all right, is going to equal the normal force times mu for static friction. And this thing is not sliding. Like, that's the whole problem, is without sliding. So that's why it's static friction, not kinetic friction. And the normal force we've already determined is 14,700. And the mu, the coefficient of friction for static friction between rubber and asphalt or concrete or whatever is going to be, hold on, let me look that up, is actually 1. It's 1. So the frictional force is 14,700. All right, now, the sum of the forces in the R direction is what we're going to be concerned about. And it is equal to what? It's equal to 14,700. That's the frictional force. Notice it's positive 14,700, even though it's pointing to the left. Left is not negative here. It's this toward the center is positive, and left happens to be toward the center here. So left is actually positive in my drawing here. So positive 14,700 is the only force happening in the R direction. And that's going to equal MA. That's equal to MA in the R direction. Okay? What is M? M is 1500. And so I can find my radial acceleration, or centripetal acceleration. Just divide, and that will give me, just a second here, it actually is 9.8, interestingly. And so what does it want to know? It wants to know the maximum speed. Well, that's tangential velocity. Can I get tangential velocity from what I've got now? Yes, because the radial or centripetal acceleration is always equal to v squared over r. So v squared over r. What is r? Well, it tells me that in the problem. The curve of radius 50 meters. So over 50 equals 9.8, and now I can solve for v. Multiply by 50, take the square root. .14. So v equals 22.14 meters per second. And we could convert that to miles per hour if we need to. Might give us a better idea of how fast it's going, but we won't, unless we just had to for the problem's sake. Okay, here's the problem as described in the PowerPoint presentation from the publisher. Sure doesn't make these things too small. I wish those things were bigger. It's got the same thing we've got going on here. And it got 22 meters per second. And that's what we got, so that's good. And it says 22 meters per second is about 45 miles per hour. So 45 miles per hour is the highest speed you could go around that particular 50-meter radius curve without sliding. And that's assuming there's no wetness on the road. Also assuming that the curve is flat, not banked. If it was banked toward the center so that your angle was toward the center of the circle, you could actually go faster without sliding because it would increase that force inward. All right, banked curves. All right, it says real highway curves are banked by being tilted up at the outside edge of the curve. The radial component of the normal force can provide centripetal acceleration needed to turn the car. For a curve of radius r banked at an angle theta, the exact speed at which a car must take the curve without assistance from friction is given by this little formula right here, which you could memorize, but I don't memorize that. I usually just figure it out with the problem. So we get to example, I'll hopefully be able to show you what I do. Here you can see what it means by a banked curve. So there's a normal force that is going to point in this direction right here. So if we're looking at RTZ, there's Z, there's R, you can see that the normal force will have a component in the R direction. If it's tilted like that, it will have a component in the R direction and another component in the Z direction. So this component in the R direction there is going to provide extra centripetal force to help the car go around the curve. Consider a car going around a banked curve at a speed slower than that maximum speed. In this case, static friction must prevent the car from slipping down the hill. See, if you're not going around the curve at enough speed, then actually static friction the car would want to slide down the hill if there was no friction. So static friction would actually point up the hill in that case. Instead of pointing towards the center of the circle down the hill or whatever, then it would point away from the center of the circle with some component of it because it would point up the hill. If a car was going around the curve faster than that max speed, then the static friction, the max speed is actually talking about the maximum speed that it could go if there were no friction, just only due to the bank of the curve, if there was no other force, no friction. If it was going faster than that maximum speed, then friction would come into play because the car would then want to slide up the curve, up the bank, so static friction would prevent that, so static friction would point down the bank, down the curve, and so it would actually help point toward the center of the circle with one of its components. Quick check 8.5. Car turns a corner on a bank road. Which of the diagrams could be the car's free body diagram? Alright, you have a normal force. Which way does the normal force point? It points perpendicular to the surface. So since the surface is angled, the normal force is going to point perpendicular to it, so like that. So that makes any of these look good. Which way does gravity go? Gravity always goes toward the center of the earth, so that makes A, B, and E be possibilities. Which way will friction point? Friction will point either up the curve or down the curve. Up the bank, I should say, or down the bank. So it wouldn't be A or B, because A or B has friction not pointing up or down the bank, but just kind of pointing in a horizontal direction. So choice E has it pointing at least down the bank. So choice E would be the only possibility here. Okay. Circular orbits. The figure shows a perfectly smooth, spherical, airless planet with one tower of height h. So there's this planet. You have a super tall tower, obviously, if it's comparable to the size of the planet right there. A projectile is launched parallel to the ground with speed v0. So imagine standing on top of this super tall tower and launching a projectile, throwing a projectile straight off the building, straight, like parallel to the ground. If v0 is very small, as in trajectory A, it simply falls to the ground along a parabolic trajectory. This is the flat Earth approximation. Okay. But as you make that velocity get bigger, the ground is curving. Actually, the ground is curving away from the projectile because the Earth is not flat. So when we have very small velocity, relatively small velocity, and it goes a relatively small distance compared to the size of the planet, we always do our approximations as if the planet's surface was flat because it's so negligible. But if it's higher velocity and going a greater distance compared to the size of the planet, that no longer holds. Like the ground is curving away from the projectile. So that would need to be factored into the calculation. Look, see, on projectile B, it's going so fast it goes a quarter of the way around the planet. In C, it goes halfway around the planet. Finally, this is getting to the point. And if with path D, you've thrown the speed is so great, or it's at the perfectly right velocity, that it just continues to fall all the way around the planet, and it will continue to do that, and that is what creates an orbit. So it says this projectile falls all the way around the planet because the curvature of its trajectory matches the planet's curvature. And that is what orbital motion actually is. It's like a continual falling all the way around the planet so that circular arc that it makes, it's not a parabolic arc anymore. It's a circular arc. And all of these are actually kind of circular, but just compared to the surface of the planet. But it just kind of depends on the distance of the flight relative to the size of the planet, of whether we count that. Alright, so this circular arc matches the circular surface of the planet. As the initial speed v0 is increased, the range of the projectile increases as the ground curves away from it. Trajectories B and C are of this type. If v0 is sufficiently large, there comes a point where the trajectory and the curve of the Earth are parallel. In this case, the projectile falls, but it never gets any closer to the ground. It falls without getting any closer to the ground. And that's what's called an orbit. Circular orbits. In the flat Earth approximation, which is demonstrated here in figure A, the gravitational force on an object of mass m is mg vertically downward. So you got this, what we approximate to be a parabolic trajectory. And if the Earth was flat, it would truly be a parabolic trajectory relative to the Earth surface. But if it's curved, if the surface itself is curved relative to that surface, it wouldn't really exactly be a parabolic trajectory relative to that surface. Since actual planets are spherical, the real force of gravity is toward the center of the planet. So Fg here always points down toward the center of the Earth, but if we took the curvature of the planet into consideration, Fg would slightly change its direction, right? Because in order to point toward the exact center of the planet, Fg would have to slightly change its direction as it goes to, in order to continually point toward the center, which is what this shows. The force of gravity points toward the center here. Notice it's going this way, but to point toward the center here, it's got to go that way and that way. And so Fg for a circular orbit is constantly changing its direction. With the flat Earth approximation, we don't have to worry about that because it's just kind of a negligible change. Alright. An object in a low circular orbit has an acceleration of this. Well, it's g. It's the same acceleration as the acceleration due to gravity. If the object moves in a circle of radius r at speed v orbit, the centripetal acceleration is equal to v squared over r, which is also equal to g, as we've already kind of said in this case. The required speed for a circular orbit near a planet's surface, then, neglecting air resistance, is just solving for v here, multiply by r, take the square root, it's the square root of rg. Alright, the period of a low Earth orbit satellite is the circumference of the planet divided by the orbit velocity, which, if the orbit velocity is the square root of rg, I'm going to show you the algebra of how to get from here to there. So it's 2 pi r over v orbit. V orbit is the square root of rg. So to get the kind of the algebra trick to do that would be if you square everything, that would be 4 pi squared r squared over rg, so that would cancel out the square root. Now the r can cancel with that r squared, and that becomes just an r. Now I'll take the square root of everything again, and that becomes a 2, and then a pi, and the r and g are still under the square root, so square root of r over g. And that's how they get to there. So this is the period. That means that's how long it takes to go in a full orbit. If r is approximately the radius of the Earth, in other words, it's a low circular orbit, where if the radius, in other words, the distance of the satellite from the center of the Earth is low, if the satellite is kind of close enough to the surface of the Earth, then it's approximately equal to the radius of the Earth itself, then t is about 90 minutes. In other words, the period for a satellite going around the Earth is somewhere around 90 minutes. It's amazing that a satellite is going all the way around planet Earth in an hour and a half. That's amazing. An orbiting spacecraft is constantly in free fall, falling under the influence only of the gravitational force. This is why astronauts feel weightless in space. This International Space Station, where the astronauts are in there, they feel weightless because this thing is constantly in free fall. Alright, centrifugal force. We've already talked about this. The figure shows a bird's eye view of you riding in a car as it makes left-hand turn. From the perspective of the inertial reference frame, the normal force from the door points inward, keeping you on the road with the car. So you're trying, your body tends to want to go in that straight line, but the door keeps you moving toward the center of the circle. The door provides that central force that makes you move in the circle, that centripetal force. Relative to the non-inertial reference frame of the car, you feel pushed toward the outside of the curve. So the car is accelerating. So an inertial reference frame is a reference frame where everything kind of follows the expected physics. Like what you feel and what you compute are all conjoined. But a non-inertial reference frame is where that stuff doesn't really feel that way. It's like, and that non-inertial reference frames are anything where you have an acceleration. If there is an acceleration present and you're inside of that acceleration, you're now in a non-inertial reference frame. The fictitious force that seems to push an object to the outside of the circle is called the centrifugal force. So the inertial reference frame would be outside of that situation, outside of the car, the objective view, rather than the subjective view. There really is no such force in an inertial reference frame. Quick check 8.6. A coin sits on a turntable as the table steadily rotates counterclockwise. The free body diagram below shows the coin from behind. So the coin is going this way, but now this dot represents the coin, and you're looking at it from behind the coin. So imagine you're looking at the race car from the rear end of the race car. Which is the correct free body diagram for that coin? Okay, try to take your time and think of it. We have the gravitational force. We have a gravitational force and normal force, and we have a frictional force. The frictional force is keeping that coin, trying to keep that coin from sliding. The coin wants to go off in the tangential direction, so it's constantly wanting to go away from the center of the circle. So, this is a good looking free body diagram, but look at A and C, they look exactly the same. There's one big difference. It took me a second to see it, but in C, look, the R-axis, the symbol for the R-axis is here, whereas in A, the symbol for the R-axis is here. This means it's the positive R-axis, and the positive R-axis should be toward the center of the circle. So C is the correct one, A is not. Quick check 8.7. The coin sits on the turntable. What force or forces act in the plane of the turntable? In other words, what forces as you look down on it are acting in this plane? It says it rotates steadily. That means it's at a constant speed. It's uniform circular motion. That means there is no acceleration other than the centripetal acceleration pointing toward the center of the circle. That means it has to be A. The static friction keeps that thing going around this curve. It always points toward the center of the circle. Static friction would not be, if this thing was accelerating around the circle, then there would be some sort of a static friction pointing one way or the other, but it's not. It's not accelerating. It's going at a constant speed, so A should be the right choice here. Alright, similar. Two coins are on a turntable, starting from rest. Which coin flies off the turntable first? This is kind of the merry-go-round question. If you've ever ridden on a merry-go-round, where is it harder to hang on? If you're toward the center of the merry-go-round or if you're toward the outside of the merry-go-round. We do a free body diagram where this is the frictional force. The sum of and we have gravity and normal force, but the sum of the forces in that R direction is just the frictional force. That's going to equal M omega squared R. So the frictional force is going to have to be bigger when R is bigger, right? If R grows, the frictional force is going to have to grow. If the frictional force can't grow, if it's the same thing, then the bigger R gets, the more that it's going to overcome friction. So since object 2 is farther away, it's going to have a greater frictional force to keep it from sliding. So I think object 2 is going to fly off the table first before object 1 will. Yep. Interesting slide here. Gravity on a rotating Earth. Figure shows an object being weighed by a spring scale on the Earth's equator. Okay. We have an observer in an inertial reference frame that's not moving. He's just kind of hovering over the North Pole in this case. If we pretend the spring scale reading is F spring scale equals Fg equals mg, this has the effect of weakening gravity. The free fall acceleration we measure in our rotating reference frame is this. So, in other words, it's kind of like the coin on the table. If the coin is farther from the radius of rotation, the center of rotation, then it's going to have a greater force needed to keep it going in that circle. So in other words, you're going faster around, right? Like this guy, his omega, his angular velocity, the angular velocity of these two guys is the same. Because, at 90 degrees, they're both the same place. At 180, they're both 180, so they have the same omega. But their tangential velocity is not the same because V is equal to omega R. So the bigger R is, the bigger V will be. So object 2 is going to be have a greater linear or tangential velocity than object 1 will have. So the farther you are from the center of rotation, the greater your tangential velocity will be. And so if you are on the equator versus being up here in North America or on the North Pole, you're farther from the axis of rotation. If you're up here on the North Pole, you're on the axis of rotation. If you're down here on the equator, you're the farthest you can get from that axis of rotation, which is going to make your velocity be the biggest, which is going to make the effect of the scale is going to read the least when you're standing on the equator than it will if you're standing somewhere other than on the equator. Now, your mass is going to be the same, so it ain't like you actually lost weight or lost mass or anything, but the reading on the scale will be a little less than it will be if you are somewhere else. All right, loop-the-loop, like a roller coaster here, going around the loop. The figure shows a roller coaster going around a vertical loop of radius r. note this is not uniform circular motion. It is not uniform. Uniform circular motion is when you're going the same speed the whole time. That's not the case when you go on a loop-loop. When you go on a loop-loop, you're going fastest down here and the slowest up here, and then faster down here again. At the very top, so the car slows down going up one side and speeds up going down the other. The very top and very bottom points, only the car's direction is changing. So the acceleration is purely centripetal at the very top and very bottom points. Only the car's direction is changing. Because the car is moving in a circle, there must be a net force toward the center of the circle. Alright. Consider the roller coaster free body diagram at the bottom of the loop. Since the net force is toward the center, the normal force must be greater than gravity. That's why you feel heavy at the bottom of the valley of a loop-to-loop. Or the bottom of the valley on any roller coaster. Sum of the forces in the r direction is equal to the normal force plus the gravitational force, where the gravitational force is negative, so it's normal force minus mg equals ma sub r. So the normal force is equal to that. The normal force at the bottom is larger than gravity because it's if you move mg over, it's mg plus whatever this mv squared over r is. So the normal force is larger than gravity at the bottom, but at the top, the net force has to point toward the center still. So the normal force has to be less than gravity. Figure shows the roller coaster free body diagram at the top of the loop. The track can only push on the wheels of the car. It cannot pull. Therefore, the net force presses downward. The car is still moving in a circle, so the net force is also downward. So if you look at this, now, again, because r, the positive r direction, is toward the center of the circle, now gravity is a positive value instead of a negative value. Like down here, gravity points toward the center of the Earth. The center of the Earth is away from the center of the circle, so gravity has a negative value. But up here, gravity still points toward the center of the Earth, but now the center of the Earth is toward the center of the circle, so gravity has a positive value. So the normal force plus mg equals mv squared over r. Subtract mg from both sides, and now the normal force equals this mv squared over r minus gravity. So that probably means the normal force is going to be less than gravity, but it could exceed gravity if mv squared over r is big enough. If mv squared over r is big enough, then if you subtract gravity from it, m could still be bigger than gravity if this first term is big enough. Now, so this is the normal force at the top of the loop. As this term right here decreases, there comes a point where this is going to equal this, and the normal force will then equal 0. If the normal force equals 0, that means that there is no contact between this roller coaster and the top of this track. That means this thing is actually coming off the track. It's the point where this thing begins to come off the track. That's called the critical speed. Where the normal force equals 0, that's called the critical speed. That's the slowest speed at which the car could continue to complete that loop, because it's the speed where it will begin to lose contact with the track. Any slower than that, and it's going to fall. Any faster than that, it's going to continue to make the loop. But that's the critical speed where it has to be. Any slower than that, it's not going to make it. That's the slowest speed at which the car can complete the circle without falling off the track near the top. Okay, roller coaster at the top of the loop. Normal force adds to gravity to make it a large enough force for the car to turn the circle. At the critical velocity, gravity alone is enough for the force for the car to turn the circle. If the speed is not enough, the gravitational force is too large for the car to stay in the circle, and it's going to fall. Quick check 8.9. All right. A physics textbook swings back and forth as a pendulum. Somehow you've got a string or something attached to this physics textbook so it's swinging back and forth. Which is the correct free body diagram when the book is at the bottom and moving to the right? All right, the only forces acting on this book are tension and gravity. So D and E can't be right. So which one of these is it? The question is the tension greater or is gravity greater? Or are they equal? At the bottom of the loop, in order for this thing to continue moving in a circle, the net force has to point toward the center of the circle. So for that to be the case, the tension has to be greater than gravity. So C has to be the right choice there. All right. Car that is out of gas coasts over the top of a hill at a steady 20 meters per second. Assume air resistance is negligible. Which free body diagram describes the car at this instant? It's coasting at a steady 20 meters per second over the top of that hill. Since it's going at a steady 20 meters per second, we can assume that there is no net force in the horizontal direction. So D and E can't be the choice. See, I wish it had said assume friction is negligible, because I would want to put a friction force on here. But we're just going to assume that because it says it's moving at a steady 20 meters per second. So if that's the case, friction can't do anything. So the only things we're going to look at then are the normal force and gravity. So it's got to be A, B, or C then. How do the normal force and gravity compare in this case? If this thing is going to move in a circle, the net force has to point where? It has to point toward the center of the circle. In other words, it has to point down. So that means gravity has to be larger than the normal force for that to happen. So choice A has to be the right choice. Alright, quick check 8.11. A roller coaster car does a loop-the-loop. Which of the free body diagram shows the forces on the car at the top of the loop? Rolling friction can be neglected. Okay, thank you for saying that. Alright. So, if the rolling friction is neglected, the only things that are occurring here are gravity and normal force. Which way do they point? Gravity points toward the center of the earth, so it has to be down. Normal force is always perpendicular to the surface, so it has to point down also. So it has to be E, and they both point down, they both point toward the center of the circle. They're both helping this thing to continue in its circular arc. Notice on the previous problem, the normal force pointed up because the car was above the surface, so it had to point up perpendicular to the surface. On this one, the car is below the surface, so it has to point down perpendicular to the surface. Alright, non-uniform circular motion is next. We're going to stop right here and make another part 3 video. Well, I just said that, but I changed my mind because there's not many slides left, so I'm going to go ahead and finish. Non-uniform circular motion. The figure shows a particle moving in a circle of radius r in addition to a radial force component required for all circular motion. This particle experiences also a tangential force component and hence a tangential acceleration. So this thing is not going a steady speed around the circle. It is either speeding up or slowing down as it goes around the circle. That means it has to have a tangential acceleration as well. A tangential acceleration that's either speeding it up or a tangential acceleration that's slowing it down. Maybe it's a race car that's accelerating around the track, or maybe it's a ball going around a roulette table that is experiencing friction, so it's slowing down as it goes around the roulette table. Either way, you have a force in the R direction pointing that way. You have a force, in this case, in the T direction pointing that way. So now the net force no longer points toward the center of the circle. The net force points this way. Halfway, well, not halfway, but somewhere between the R, and the T direction. Here are the dynamics of non-uniform circular motion. Force and acceleration are related through Newton's second law. The net force in the R direction is still mv squared over r, or m omega squared r, which is, those two things are the radial acceleration. The net force in the tangential direction is mass times the acceleration in the tangential direction. And the net force in the z direction, that's going to be like a race car going up in the air off the track or sinking down into the ground to the track, but that's not going to happen, so the net force in the z direction is still 0. Here's a problem-solving strategy for circular motion problems. Model the object as a particle, make other simplifying assumptions, use RTZ coordinates. R-axis points toward the center. Show important points in the motion on a sketch, define symbols, blah, blah, blah. Free body diagram is the key here with the RTZ coordinates. Determine the force components of the free body diagram. Be careful with the signs. Yep, be careful with the signs. Anything pointing toward the center of the circle is positive in the R direction. Anything going counterclockwise is positive in the T direction. If it's going away from the circle, the center of the circle, it's negative in the R direction. And if it's going clockwise around the circle, it's negative in the T direction. Alright. Quick check 812. The ball rolls counterclockwise around the inside of a horizontal pipe. The ball is fastest at the lowest point, slowest at the highest point. At the point shown with the ball moving down, what is the direction of the net force on the ball? This thing is moving counterclockwise. It's slowest up here and it's fastest down here. That means it has to be accelerating this way as it goes down this circle. So that means it has to have a tangential acceleration as well as a radial acceleration. So the net force is going to point. Let me draw that for you. It has a force in the tangential direction. It also has a force in the radial direction. So the net force would have to be something like that. Well, it would be the addition of these two forces. So that plus that, or that plus that. So this would be the net force right here. So I'm thinking it's choice D. And it is. Alright, that is the end of the PowerPoint. Chapter 8 summary slides. Feel free to pause this at any moment when you want to look at something more closely. I'm just going to scroll through it. Alright, good luck on Chapter 8 homework assignment. Text me if you have any problems that you are struggling with, and maybe I can make a video about that individual problem. Hope to see you sometime soon in class.